looking at exercise 4F2, nth roots of unity. I've written that up here. Mostly I want to just talk about the idea. And also you're going to notice in these questions the use of W. And you might be initially thinking, why would we bother? But basically, solving some complex number to the power of n equals 1 is very simple. Let's say we had, I don't know, 6 and it equals, so some complex number to the power of 6 equals 1. Right. Now one of the solutions is 1. I'm going to try and draw a Argand plane and a circle at the same time. So there's my Argand plane. Because we've got 6 roots and we've previously learnt that they'll space themselves evenly around the circle, the first one will be at 1, and then I basically just need to break up my space here, 2 pi, into sixths, right? So I'll be here, then here, here. I need to do this 2 more times and then we've got them all, right? This angle in here is 2 pi broken up into sixth, which ends up being pi on 3. This will be enough for me to start getting solutions. I root 3 on 2, etc., etc. This one over here is -1. And I could go around and find all those roots quite quickly. So that's the idea in this section, that finding solutions where you have a unity or equal to 1 is pretty straightforward. What we've done previously is we would have said this is cos, why am I writing cos? Sorry, cis, right? Cos I sine 0 plus multiples of 2 pi. Multiples can be expressed with k. And then we would have applied de Moivre's theorem to this. Cis, I'll get rid of the 0 now. K 2 pi. We would have taken the 6th root on both sides, and this is where de Moivre's theorem comes in, and you can say, all right, I've got cis of k multiples of 2 divided 6 pi. Right, and just a reminder, you're supposed to be writing de Moivre's theorem when you use it. And then I'd go around and I could see that I just keep moving by pi on 3 every step of the way, and I find my 6 roots. After you've done that enough times, we don't have to worry about the modulus changing here or anything like that. It's just 1. So the length of these roots is 1. The first root will start at 1, and that's fairly obvious. I think 1 to the power of 6 is 1. So if you can create a form like this, finding the solutions is very quick and easy. And what we do, I was going to say this later, but I might as well say now, because we're too lazy to write, to list them all out. You got cis 0 here, you had cis pi on 3, then you had cis 2 pi on 3. When you get to cis 3 pi on 3, you're probably just going to write -1 at that point. Cis 0 is your 1, right? But and there's 2 more after that. But to save time and make things a bit quicker and easier, we say, well, the first root is 1, and then we'll have w and w squared and w cubed, and I would need to go up to w to the power of 5 in this instance. All right, so the first root is 1, and then you've got 2, 3, 4, 5, 6 roots total. And what you're doing is you're saying let w be cis, well, in this instance, 2 pi divided by 6, although obviously that's just pi on 3. All right. So you can get to this first w quite easily, because you're just thinking, well, I've got the circle 2 pi radians, and I'm just going to divide it into 6. Basically the w is going to be the smallest angle here, so I'm focused here, you can see my cursor. And why is the other roots w squared, w cubed? Because you just keep rotating round. So this one here was cis pi on 3. All right, I'm saying that this next one, w squared, will be cis pi on 3 times cis pi on 3. All right, and we know that the arguments add, so you get to cis 2 pi on 3. Right? Or you could use de Moivre's theorem, and you could say, you know, this is all equivalent to saying cis pi on 3 squared, right? And then so the power of 2, you would multiply your argument by 2 to get 2 pi on 3. And that's going to keep going. When I go to w cubed, I'm effectively just multiplying by cis, and these multiplications, I'm multiplying by cis pi on 3, I should say. You know, so let's consider the w cubed, this one. Right, so the way it's working is I'm defining w as, I guess it's the second root. It's the root with the smallest angle, is a nice way to think about it. So your first root, just write 1. I wouldn't be writing cis 0. You then define your next root, w, using the smallest angle, and then all of your other roots are just going to be powers of w until you get to 6 roots, because I had z to the 6. Right. So it's very simple. It's almost like I can jump from seeing this z to the 6 equals 1. And I can think, all right, well, what are the roots? 1. Then my first, my w will be 2 pi, but divided by 6. Okay, so I need to let w equal cis pi on 3. All right. Now I know what w is. I'll make a little note of that. Let w equal cis pi on 3. And it just makes it easier to, w squared, and so on until you get to 6 roots. So hopefully you followed all of that. Let's solve something like I solved yesterday, actually. Well, we might do, so we can compare. And it's very similar. But what we're trying to do is make, this eraser is very frustrating. It'll take me ages to clean the screen. I'm thinking of, maybe I'll write it down so you're not getting bored. I'm thinking of, what if we had z cubed equals 8, right? And the technique is, let's make it equal 1, because roots of unity are so easy to work with. Right? Get rid of that. I'm just going to a cubed. Too many W's. Okay, so you can be trying to solve this at the moment, but using this idea of roots of unity. So this is how it would work. This question's quite straightforward. You can apply this idea to more complicated equations. I could say, well, z cubed here, I've deliberately made a cubed number on this side to make things a bit easier. I could say, well, this is z cubed divided by 2 cubed. Right, the 8's just a constant number there, so I can write an 8 as a 2 cubed, no problem. And then I'll leave my 1. Here I've divided by 2. We can put all this into 1 power, like so. Right, we could, if we want, say this is cis 0 plus 2 pi multiples. Right, but I don't think I'll even bother. I'll just say we've got z divided by 2, and I'm going to take the cube root of both sides. So it's 1 cube root. Maybe I should write it as cis probably. But what I'm trying to impress on you is that I can write this pretty easily. I need to know that w is 1/3 of a circle, so 2 pi divided by 3. So let the w equals cis 2 pi on 3. It might help with a diagram to see what's happening. Try and draw a circle on the Argon plane again. Colors. All right, so the first root was 1. Then I needed 3 of them, so I'm going thirds around my circle, like so. I'm defining w based on the smallest angle, 2 pi on 3. I can get to these values, and in this instance there's conjugate pair in the roots, which is interesting. There are a few interesting things about the roots I might mention. Now, this isn't quite finished, of course, because of the divided by 2, so which I haven't dealt with. I've found z divided by 2, not z, so moving on from that, I'd be saying that the actual z values would be 1 times 2. I've got it, let me just, if it's not clear, I'll write it. We've got this statement at the moment. Complex number z divided by 2 equals 1 w or w squared, right? So therefore, what is z? We'd have to multiply everything by 2. So what's 1 times 2? I reckon I can do that. 2, right? This will be 2w, and this will be 2w squared, right? The roots are 1 and 0i here. Over here we've got our cos value is 1/2, and our sine value is √3 on 2i. We've got modulus of 2 for these, so I might tidy that up. We've got 1 and √3, and that should be negative, of course. So we'd have, where's my pen gone? -1 plus I √3. And down here we've got its conjugate pair. The angle's 4 pi on 3. So that would be -1 minus I √3. Okay, so those are your 3 roots. If you cube, I didn't multiply this one by 2. I was still looking at unity, but I'm now multiplying everything by 2 to actually find the roots of 8. So this first one, 2, if you take any one of these roots and you cube it, you will get the answer 8. Also worth noting is that if I multiply the three roots, so say I've got z1 times z2, that could be z2 there and z3, you will get 8 that way. You can see some of these results by thinking about rotations on the Argand plane as well. Here's an interesting one. If I took one of the roots, let's maybe pick this one, and I squared it. So let's say I squared that, it would equal this root times this root, which is an interesting result. And you could sort of determine that by thinking about these rotating around. So if you did this root times that root, you'd have to take this and you'd have to add on 4 pi on 3, which would get you here. You'd also have to double the modulus and you'd be out there. If you took this root here and you squared it, well, this root's got an argument of 2 pi on 3, so you'd be rotating another 2 pi on 3. This has a modulus of 2, and it would now have a modulus of 4 once you squared, 2 squared's 4. Right? And that pattern will hold anywhere. If I took this root and square it, it's the same as timesing this root by this root. So there's some nice little things to notice in the roots, which can be explained really easily if you've got this Argand plane in front of you and you're thinking about multiplication resulting in rotations of the argument. If you've got a modulus of 1, you don't have to worry about the results increasing their magnitude because your moduluses are all 1 times 1 times 1. I think I'm starting to babble a bit now, but I reckon I've covered most of what I want to cover. There's another type of question that you might get where we would just sort of complicate things on the left. So if you bear with me, I'm going to need some time to erase. Am I on black? What if I said something like, I don't know, 2z, what if we did -1 divided by 3 all cubed is 8, and we want to find z. So we can use the roots of unity idea here as well. Maybe it's unnecessarily complex. Might just simplify it. We'll just do that, just to get the point across and not spend too much time on the video, because I'm trying to keep these videos short, but they're tending to go a little bit longer than they need to. I suppose you guys can play them on fast forward. You can increase the speed to 1.25 times. If only I could record them like that. So what I'm saying here is 2z minus 1 all cubed. What I want to do is divide it by 2 cubed, because the 8 is 2 cubed, and that will leave me with 1 behind. And I've got cubed and cubed, so I can put it all into one under 1 power, like that. All right, I know from experience that these are how this is going to play out. I'm going to have 2z minus 1 on 2 equaling 1 w squared, where and w is cis 2 pi on 3, so I'm just taking the circle, dividing it up by 3 because there's 3 roots. I've got unity, so I don't have to worry about modulus or anything like that. So there's my 3 roots. I can then work with this a bit more, and I could say, all right, well, 2z minus 1 would have to equal 2w squared. So what have I done there, people? So I've times everything by 2 to get rid of this divide by 2. We need to add 1. Okay, so what's 2z? We get to add 1 to everything. 3, 2w plus 1, w squared plus 1. And now we need to divide by 2. So we get 3 on 2. We get 2w plus 1 on 2. And we get w squared plus 1 on 2. All right. And basically what this is saying is if the z value is 3 on 2, if I could take it back here, you know, what's 2 times 3 on 2? It's 3. 3 minus 1 is 2. 2 cubed, yep, it works. It equals 8. What about this third root would be w squared plus 1. So that third one is equivalent to cis 4 pi on 3 plus 1 all divided by 2. I could work out what that was if I want. You know, use your calculator or break it up into cos and sine. Then if you cubed it, you will, not if you cube it. You've got to take that result and then you've got to put it back here. So you'd have to times it by 2, subtract 1, cube it, and you'll get 8. So hopefully that all made sense. Roots of unity, really easy to work with. And the W can save you a bit of time. Just read the question carefully. So if they're asking you to express with W, where W is cis smallest angle for theta, do that. Some of the questions ask you to draw the Argand plane and show that, you know, in this instance, the 3 roots and where they are. Some might ask you to convert into the you know, the regular complex number form with cos plus I sine theta, or turn it back into a cis form. So just read those questions carefully, but this stuff is fairly useful and fairly easy to work with, these roots of unity, and hence that's why you're learning about it. Okay, I'll leave it there. Hopefully you are keeping up to date with your questions.